Hello everyone, this is group 16 and we are going to talk something about IoT protocols today. Well, actually we have already seen some IoT protocols from the lecture. For example, we have already seen LWM2M for the application layer. Well, this is good. We also have seen COP for the transmission layer. It's also good. But, well, we have come to a problem that what do we have? What are the protocols we have in a lower layer, like the physical layer and the MAC layer? Well, let's first take a look at some conventional MAC and physical layer protocols. Let's say we have a Wi-Fi, we have Ethernet, and we have Bluetooth. We would say they are all good protocols because we use them every day. But are they suitable for IoT environment? Are they suitable for those endpoint devices that need a long-range communication and only with low data rate and low power consumption? Let's take Wi-Fi as an example. We say Wi-Fi is not that suitable for IoT environment. This is because, first, Wi-Fi is short-ranged. If you stand in a home station, you are not that possible to receive the ToE guest signal, although they are less than 1 kilometer away. Typical Wi-Fi signal cannot spread beyond 100 meters, which is far too short for IoT devices. Second, Wi-Fi has a very high data rate. If you have downloaded a game from Steam, that you may notice that your network can reach several megabytes per second. Such a data rate is, well, really good for our PC users, but it is obviously too high for IoT devices. And finally, it also leads to a very high power consumption. So, in conclusion, Wi-Fi is not an ideal protocol for IoT. Then we come to our problem that how to find a suitable physical or MAC protocol for IoT such that it has a long range, fair data rate, and low energy cost. To evaluate our such solutions, we made a list of requirements. The above three are major aspects, where range needs to be long, data rate should be high enough for transmission but also not be too high, and cost as less energy as possible. The below three are additional or sub-aspects. We first expect the protocol is accurate, and the device involved has a long battery lifetime, and of course, the protocol should have a high scalability. Here we have introduced our problem and way of evaluation. Now let's come to a possible solution. Low power wide area networks, or in short LPWAN, is a technology to build transmission protocols with features of long range, low data rate, and low power consumption. Although we call LPWAN a technology, LPWAN is more likely to be a kind of framework. There is not an exact protocol called LPWAN, but there are quite a lot of protocols implemented. Well, due to limitation in time, we have introduced two most outstanding implementations, LoRa and Sigfox. Let's first take a look at LoRa Alliance. LoRa Alliance, or in short, LoRa, is a family of MAC physical protocols and technologies achieving long-range, low-power transmissions. The most significant point of LoRa is it uses a special technology called SSM, which stands for Spirit Spectrum Modulation, instead of traditional FSK on radio signals, so as to save energy physically. Then, let's come to its architecture. A LoRa network uses star topology and consists of 5 types of objects, which are end nodes, gateway, network server, application server, and clients. Well, on the map here, on the map of slides, clients are not shown on the screen, but it should be on the rightmost. An end node sends message to multiple gateways, but due to the star topology, every node does not receive messages from each other. Then the gateway forwards the message to the cloud, or let's say the network server, and the cloud transfers these messages to application server and finally to the client. It is noticeable that all the components in the network should be in cloud all the time in order to receive real-time message. So much for technique. Let's discuss LoRa's performance. First are some main aspects. Well, official documents have never mentioned the working range of LoRa, but by a formal report from Synth company, its range is claimed to be 5 to 15 kilometers. Another investigation from IEEE insisted that the number should be less than 11 kilometers, so we believe that it should be about 10 kilometers. Same report from Synth pointed that power consumption of LoRa should be 14 dBm in Europe. This is not the case in North America because of the different radio frequency, but the details are beyond our topic today. A typical LoRa data rate is 0.3 to 5.5 kilobits per second. Meanwhile, some specific settings can make the value up to 11 kilobits per second. These numbers are based on SSM channel. However, LoRa also accepts the traditional FSK channel, which has a data rate of 50 kilobits per second at a cost of higher energy consumption. However, LoRa still has some problems. The most noticeable one is every node and every component in the network needs to be in the cloud all the time so as to transmit information. This prevents LoRa from being lightweighted and severely limits its mobility, which can be a serious problem. Besides, there are no guarantee in quality of service. There always be a trade-off between delay and quality. For normally, we use acknowledgement to detect whether a message is received, but the acknowledgement itself is also a message and increases the delay if there is any in the network. LoRa has nothing to guarantee the quality. This, without doubt, improves its performance, but somehow may bring some other problems. Then let's come to Sigfox. Sigfox is the world's leading provider of dedicated connectivity for Internet of Things. It is designed to meet the requirements of mass IoT applications, long device battery lifetime, low power, high network capacity, and long range. Sigfox is the biggest competitor of LoRa, and of course it uses ultra-narrow-band approach, which makes the Sigfox accommodate more channels in the same space compared to LoRa. Due to this, Sigfox will make use of physical channels more efficiently, hence more network capacity can be achieved. Sigfox is a lightweight protocol dedicated to handle small messages. For the same payload data to transport, Sigfox will use much less overhead. Since a signal is made of energy, the more data is transported, the more energy will be needed, even for overhead. As for Sigfox, there is less data to be transmitted, less energy is needed, and hence battery life will be extended. In addition, using less overhead means more space for user data to be transported, and hence this will increase the network capacity to a great extent. Sigfox enables device to send wirelessly very small messages, which is 12-byte data payload and few messages per day, which is 140 messages per day. Thus, the battery life could be extended. And finally, Sigfox achieves long-range communication by relying on a very low data rate of 100 bits per second, which is much less than the data rate of LoRa, which commonly is 0.3 to 50 kilobits per second. Such a low data rate results in great sensitivity, which allows for long-range communication of multiple kilometers. And then let's take a look at Sigfox network architecture. Sigfox network consists of objects, Sigfox gateways or stations, one and only Sigfox cloud, and IT servers. Objects are connected with stations by using star topology and transmit their messages to the Sigfox network when the radio signal reaches the stations within the range. With the direct secure point-to-point link existing between Sigfox stations and the Sigfox cloud, the stations could detect, demodulate, and report the messages to the one and only Sigfox cloud. The cloud interfaces with IT servers using different protocols such as SNMP, MQTT, and so on. Now we take a look at the main and sub-aspects of Sigfox to see its pros and cons. Thanks to Sync report, the aspects could be analyzed quantitatively. Sigfox works in a very low data rate with 100 bytes per second for uplink and limited data per day for downlink. Sigfox makes the message could be received even 100 kilometers away in rural under the idle condition, which is much longer than LoRa. Power consumption of transmission with Sigfox is up to 20 dBm, which is a little larger than LoRa in Europe. Sigfox provides an end-to-end security by asynchronic encryption. Though no further technical details has been published, the protocol is believed to be secured. Besides, the Sigfox handles the small messages and small overhead, which leads to little power consumption. Consequently, the battery lifetime for devices could be extended to about 10 years, and the less overhead leads to more space for user data to be transported, which ensures the scalability of Sigfox. According to Smith's report, up to 1 million nodes could be handled by a single Sigfox gateway. Based on characteristics of Sigfox, the protocol has some inevitable drawbacks. First, CSMA-CA or any other technique for collision detection avoidance are not being used in Sigfox. And consequently, Sigfox technology is put under stringent transmit power, and in Europe duty cycle limitations by not being able to transmit more than 1% of the time. Besides, narrowband transmission is the worst type of interferer for other systems. A single Sigfox device could already interfere with any wideband system. And then, current Sigfox deployment only supports one-way communication without acknowledgement. This means that an application can only achieve reliability by retransmitting the same data many times in case the application did not receive it in the first place. Due to this, power consumption will increase because of retransmissions. Finally, Sigfox's data rate is so low that even sending the smallest data, for instance 10 bytes of information, requires a transmission time of about 10 seconds. Such a low data rate and long packet duration make Sigfox extremely sensitive to frequency inaccuracy and interference. Now we can access to the qualitative metrics and do some comparison and conclusions. We can see that Sigfox can achieve an extremely long range at the cost of power consumption and extremely low data rate. Both protocols have security guarantee and have a fair battery lifetime. And well, Sigfox has 4 times as large as scalability of Lower, but Lower itself is regarded with a high scalability. So we can come to some conclusions. First, both protocols fit to LPWAN features, and Lower has better data rate and lower power consumption. Sigfox has a much longer range and a better scalability, and both protocols are suitable for IoT at some specific situations. However, neither of them can be used on portable devices because they are both lack of mobility. And well, finally, a conclusion is they are not the best protocols we can find. This is because IoT is a fast developing subject. We may expect that there will exist an even better protocol than we have introduced today here in the future. So that's all we want to discuss today. And here you may see see our reference and see where we collect our information from. Uh, so that's all. Hope you enjoyed the video and thanks for your watching.